We are in part 2 of session 14 of the course on mathematical signal processing. And the key point is now to give you an idea how to prove with the definition of S0 as a Wiener amalgam space as the subspace of all those elements in the Fourier algebra, which with respect to a given BUPU, which can be arbitrary, is absolutely convergent, how to verify that this space is also itself invariant under the Fourier transform. It is quite obvious due to the Riemann-Lebesgue lemma that S0 is inside the Wiener algebra because FL1 locally is embedded into C0 locally. But if this space is also Fourier invariant, it means that we are having a space which is now inside of the Wiener algebra and its Fourier image. So in terms of my templates, our circle, this magenta circle S0, is inside what I was representing as a square in object in my function space collection. Okay, so how can we prove it? There are probably slightly more elegant ways to do it later on in different ways. The usual way would be to characterize WFL1, L1 as a modulation space and say, oh, we're talking about functions which have an integrable short-time Fourier transform, and then the rotation of a spectrogram by 90 degrees doesn't change integrability over the time frequency plane. That's the argument for this space used in the book of Charlie Gröchenik, for example. I will go back and use a variation of the original proof from something like 40 years ago, but with the additional difficulty that I'm trying to avoid Lebesgue integration theory and standard properties of L1 and L2. So that's why it maybe looks a little bit more complicated. So the first observation is we are working inside the space of the Fourier algebra because we have absolutely convergent sums in the Fourier algebra. But we are also working inside C0L1, as we have argued already several times, and that's the space which is inside L1. So we're working inside the domain for the moment where the Fourier transform is well defined, the inverse Fourier transform is defined in the pointwise sense, so no problem about changing these things. Now, in order to do the key step in the proof, we will need one more thing, which is we need plateau type functions in the Fourier transform of our space. So the space is well defined, space of decent Riemann integrable functions, and we know its Fourier transform is also a space of continuous functions, which is also integrable, but we don't know if it's small enough to be inside the original space. And therefore, for this purpose, we need on the Fourier transform side, or if you want on the inverse Fourier transform side, certain plateau types functions. Recall in the definition of FL1, little l1, we need some partition of unity generated from a bump function psi. Think of a trapezoidal function, and that's some function reproducing the function, so I call it P for plateau type function in this. So the standard way of producing that might be to just take a collection of shifted versions of the psi, so several elements of this partition of unity add up. Here I was using a slightly different argument. Using the properties of the original space or so. You are having, first of all, band-limited functions in this space S0. And this is coming from the fact that we have seen that you can you apply these Dirac sequences. So if you take a sinc square function as a Dirac sequence, that means on the Fourier transform side, we will have triangular functions and they have all compact support. Well, it's true you have to compress sinc square very much, which means that you have to stretch the triangular function very much, but you get a function which is in S0, which has as a Fourier transform which has very small support. Well, how do we get a function which has which has compact support? How do we get a function which is positive, well, you multiply it with the conjugate. So it should be either f star Fourier transform or it's f hat conjugate. If you multiply f hat with f hat conjugate, you get absolute value squared. So, well, there are in the range in this space, there are functions which have compact support and are positive. Now, we also have dilation invariance of the spaces. This was a consequence of the atomic decomposition. I think I skipped this argument. So if you have any function which has compact support, you squeeze it, you compress it in any way, and you get some function which has small support. So next point is that, and here I'm having, I have to do a correction. We know that pointwise multiplication of elements from the Fourier algebra on S0 are in S0. This is just because the Fourier algebra is an algebra, and if you multiply any atom, something in a compact support with an element which has arbitrary support, the product function has this. So please, I have already corrected this, but not in the version that I'm displaying now. So this should be pointwise multiplication, but we are living in the world now where pointwise multiplication and Fourier transform are applicable. So we take the forward or inverse Fourier transform would be more appropriate, but it doesn't matter when you have all of the spaces. You get that L1 convolved with this Fourier image is in this space. So we are using the argument that if somebody convolves something which is in the not yet fully understood Fourier image of our space, it's leaving the space invariant. And there are different ways to produce it. Now, the whole point of this proof is now the following. If somebody has the atomic decomposition in our space, so you give me an element F, which is in this space, local FL1, global L1, because the pieces F psi k are in the Fourier algebra. So you know that if you take each piece and you take the Fourier transform, it's in L1. But now I'm saying, well, I have something which lives in a box, so to say. If I shift my plateau function, which is reproducing my psi, then of course the shifted version will reproduce the shifted version of psi, which is my psi k. So I'm writing psi k as psi k times 1, which is psi k times shifted plateau function. But that's very convenient, and you see how I'm using now pointwise multiplication and convolution. Going to the Fourier transform, I can even say that, yes, this is in a Fourier transform of this guy, and instead of multiplication, I'm taking this here. Actually, I have a small mistake. I should write f of tk of p. So we should be careful now in the estimate. So what we know is that the Fourier transform here is something where this guy is in L1 and this guy is in the space where we want to be. Okay, you have this property here. So we can do the L1 S0 game and use the L1 norm of this guy here. But we know, of course, this is a translation. This is the Fourier algebra norm of the first guy. And as I said, it should be called the f of the tkp. But tk is the same as modulation of this, and the norm of all these elements is the same. So the point is, I should correct this in the final write-up or so. So we can control the zero norm, and that's very important, by the FL1 norm here. And this is happening on the Fourier transform. So you're saying, well, if I take each of those pieces, I transfer them, I find that this is an absolutely convergent sum in the norm, because this is absolutely summable. Then I can say that f hat is the Fourier transform of all these pieces. For each piece, I get one term, and I get a constant which has the shift parameter here built in, but that doesn't matter. It has the same constant here, or at least a uniform estimate here. And therefore, you can do this. And therefore, you can have pull out this constant, and you're saying this is just my original version of the norm. And therefore, up to some constant, depending on how I build the space and how I measure the norm, is controlled. So I'm getting that the space is invariant under the Fourier transform. So essentially the key is, in a more general setting, I would argue maybe that I take a function which is sufficiently smooth, maybe a test function, a Schwartz function, that is reproducing everything with this, and I have to just move it to the same position. But in the norms that we're using, this change from P to a shifted version, which are on the Fourier transform, a modulated version, does not change the norm, or it doesn't throw away the uniform control. So we have a space now which is invariant on the Fourier transform, and that's more or less all what I wanted to do in terms of theoretical things for now. So I'm stopping this, and to do something quite different, and I will see how it works. I have not much experience yet with the MATLAB. I mean MATLAB live script in combination with Zoom. So that's what I would like to do now. Next, I would like to show you, and that's really a new part of this, how to do Fourier analysis and many things that we have been doing in a MATLAB setting. I'm using my toolbox, and so it's not, you will not be able to run the same experiment yourself, but I will try. I'm willing to share these things. So the first thing is that I'm showing you the Gauss function. So I have a special command which you see here. It's called stemcil, and it means it's a stem command. So that means instead of piecewise linear interpolation of data points, you're having needles, but it's on the cylinder. So here you see quite nicely a picture that is supposed to represent a discrete Gauss function on the unit roots of order 72. And so you would say, oh yes, it's nice. Now I tried to test it, but if I do this in my standard MATLAB, I could even rotate it and look at it at different angles. But you can imagine that if you see such a graph, then the question is, I mean, where is the origin? And the x1 is written here, tells you, well, if you get the same vector in MATLAB coordinates, you're starting with the value 0, and then you go to the unit roots of order 72 in the order 0, 1, 2, 3, and so on. And at the end, the last vector coordinate number 72 would be this value. So what does it mean that such a function is symmetric with respect to this position? It means that this value and this value should be equal or so. Now, my standard command, or the NUAC standard command to get the discrete Gauss function is to use the version going back to Norbert Keiblinger's idea. And if you plot it, it looks like this, because you plot, of course, the first, the second, the third coordinate, and you have the peak value here, and that's not so nice. And that's why I like to use a different plotting routine, which is the plot C command. And if I run it, I hope you can see it. Takes a little moment. Yeah, so you see this. Maybe I should check with you if you can see it. Please, if anybody is checking with the chat, whether you can see the plot of the Gauss function in the appropriate way as you expected. Okay. Okay, you cannot see it. That's a pity. Then I have. Thank you very much. So then I will have to share another screen, maybe. Yeah, okay, I think that was my mistake. I think it should be fine now. Can you confirm, please? Okay, yeah. So the origin. So I should go back. The plot in the standard way looks like this. So it has bad ends, but as you know, it should represent a periodic function. The good version is plot C for centered, and this other command seems to not work, the stem cell command. That's a pity. I've put it into another file, but yeah, I don't want to switch too much, otherwise I'm having you have problems to see it. Now let's see. Okay, now it's a bit of confusion now, because if I see my live editor, I cannot see what's going on here. Yeah. Okay, no. Yeah, okay, so then now this is possible. Now, one thing that if I take the Gauss function, then it's made such that it's normalized. So you should in a moment see that, yeah, that this is a function which has norm 1. Now, if I'm asking you what is the norm of the FFT of the Gauss function, then for the continuous setting, you would expect that this function is equal to the Gauss function. So it should be also 1, but no, we have a number here. And I have to recall that some kind of strange here. Or maybe I'm doing this here. I'm showing you the n and what is the square root of n, just in order to convince you that we have a situation where the square root of n is exactly this number. So I have a command which I call FFT unitary, which is kind of making up for this bad factor, but this is just the FFT matrix of this here, and if you run it, then you will see, okay, sorry, I forgot, yeah, the norm of the FFT unitary version, which is 1 over square root of n applied to the Gauss function. This is really invariant. The other command that I would use here might be that I would use my comp norm command of G and FFT of G. Maybe I'm doing it the opposite direction. Otherwise, so it compares the size of the Fourier transform of the Gauss function. And you will see it's exactly the factor square root of n, but the comp norm routine is doing the same thing. I mean, it's normalizing both vectors to the same size, and then it compares the normalized vectors. And you'll see the difference of these normalized vectors is exact. This is in the range of the numerical precision. Now, the next thing I would like to produce, I'm just not sure how, yeah, here I'm getting a new line or so. I take what I call a low-pass signal of signal length n and maybe 30. And I'm doing my comparison, favorite comparison routine, maybe Gauss function and XX. So low signal is representing a low pass signal or low frequency signal with maximal frequency plus 30, which means my Fourier transform is allowed to go from 0 up to 130, and in the negative direction from kind of n down to n minus 29. So I have 30 frequencies to the left and to the right. So actually it's this space of smooth functions corresponding to the first, to kind of the lowest 61 frequencies is a 61-dimensional space. And if I run the routine, you should see F2 spec, which is hopefully coming up. Yeah, here it is. It is it's a bit too big. Here, it's too small now. Here, it is showing you a comparison of two functions. In the first line, you see the Gauss function and its Fourier transform. And you see, for reasons of comparison, I put the unitary Fourier transform. So it's the same peak value. This is really supposed to be identically, and it's using the centered plot. Otherwise, if you were to take just the FFT of a sampled Gauss function, you would get nasty objects. Now, what you also see here is a complex valued function, and the best way to do it is to look at the Fourier transform. These are random numbers and complex numbers within the range from -30 to +30, and the resulting complex valued function is now depicted as a smooth function with values which are blue for real part and red for imaginary part or so. Now, I would like to sample this function, and so what we do is, maybe I'm saying Dirac comb of size 3 is a vector which is starting with values 0 full length. Dirac comb at distance 3 is from 1 to 3 to n. These values should be put to 1. And so what does it mean to sample a function? I'm comparing now the signal, which has the name x, with its Fourier transform, so that will be the second row of our picture, with this Dirac comb pointwise multiplied with the Dirac comb of size 3. So let's see what this is giving us. Now my MATLAB window is a little bit hidden. And so it's computing in the background, and what we will see is, of course, something which is a little bit not so nice. If we would zoom in, you would see every third value starting from coordinates 0, 3, 6, and so on. But in MATLAB, it's of course first coordinate number 1, +3 is 4, +3 is 7, and so on. So these are pertained, and because we are always going back to 0, it looks like you have a graph which is filled in. I don't want to zoom in, but what you observe here is quite nice, because you're seeing something which is quite narrow, and maybe I'm doing the same thing now with the DC6. DC6, the Dirac comb of size 6 is the same thing, 1n, and DC6 from 1 to 6 to n is supposed to be 1. And then we do a comparison of XX and XX pointwise with DC6. Yeah, I hope that works as well. And you see, there is much clear separation of the samples. So you can speculate, well, if you're increasing the sampling rate more and more, maybe you're cutting off the peak of one of these narrow peaks and you don't get enough information or so. But you also clearly see what happens on the Fourier transform side. So with 6, there is a clear separation of the copies, and the proof of the Shannon Sampling Theorem, which is kind of very close now, will be, well, what is the Fourier transform of the Dirac comb? So maybe I'm doing that also, because that will explain what we are doing. We were multiplying in a pointwise sense the function with, so I would like to do this now with the signal that's kind of repeating the signal DC6, but we would like to just see what can we say about the Fourier transform of the Dirac comb itself. Does it have a Fourier transform? Now, of course, here it's a signal of length 480, and clearly it has a Fourier transform. But now let's look how it looks like. Now, what we can say already here is that the Dirac comb has a Fourier transform, and that has a value at 0. And at 0, it's of course integration against constant 1, which means, well, you have just to sum up. Now, in the size of, at the distance 6, for signals of size 480, you can have 80 zeros. So the total value, the maximum value at 0 should be 80. Why is it only 3.5? Well, you recall I was using the unitary version, so it's 80 divided by 21 something, which is square root of n. So that's why we don't have 80 here. But if you would really depict the FFT, you would see a value 80. Now, the Dirac comb has very nice properties. If you shift it by 6 or minus 6 or plus 12, it's going into itself. And we know that here it would correspond to multiplication with frequencies. So if you multiply with something which is leaving this guy invariant, now if shifting with something, the Dirac comb or the Fourier transform has to be 0 at places where you can multiply with a number which is different from 1. That's kind of why this Dirac comb is concentrated, the Fourier transform of the Dirac comb is concentrated on what will be called the orthogonal lattice. So, I mean, visually it's clear. The Dirac comb goes to Dirac comb. But what is the spacing here and what is the amplitude? And I was telling you, well, the amplitude is 80 up to this normalization. How many peaks do you see here? And you see 1, 2, 3, 4, but this is the same. Kind of a half a peak here and half a peak here, 5, 6. So whereas the sampling rate was 6, the Dirac comb is having 6 copies at a distance of clearly 480 divided by 6. So you can play the same game and take arbitrary things here. Maybe I would like to show you something different. Where's the command line? It's gone. Sorry, I'm having problems with the command line. Yeah, here. So I'm doing, just for fun. I'm doing DC7 is zeros 1n, and DC7 from 1 to 7 to n is 1. And maybe I'm doing DC12 from is zeros from 1 to n. I mean, row vector. DC12 from 1 to 12 to n is 1. So I'm doing another thing here, and I want to show you the Fourier transform of DC7 and DC12. And I run this. And of course, you will see in a moment what the difference is. And the difference is significant. Here, 12 has 12 different peaks. And the amplitudes, if you compute it, is of course 480 by 12 is 40. So the amplitude would be 40, or here it's 40 divided by square root of 480. So that's what you get here. If you do something like 7, you see here is not an artifact of the plotting, but an artifact of the counting. 7 is not a divisor of 480. So the Dirac comb here is not living on a subgroup, as you would say here, of the unitary group or of a group of unitary circles. And therefore, there is not this perfect cancellation property for the exponential functions. So that's the difference. And that's why I'm choosing some signal lengths like 480, because 480 has a lot of divisors, and maybe I'm doing all divisors of the signal lengths which are used for sorry, that was not. The signal lengths that you use for the CD player or for modern high-fi quality. Okay, maybe I have a different command. Sorry. It's 44,100. So okay, but more probably. maybe one of the harmless commands that I'm using all the time, but maybe it has been renamed. Yeah, okay, here it is. So if you go all the divisors of 480, it's a very nice number. And if you compare it with all the divisors of the nearby, yeah, it's diff and not diffs, divisors of 512, or even all the divisors of 2 to the 12, so that would be 100 milliseconds is about 4,000 samples. And then you see that the number of divisors is much smaller for pure powers of 2. So you see the spacing there much less such objects, and it's clear because all the possible divisors of a power of 2 is another power of 2. So it's a list of powers of 2 only up to the 1/2 of the signal length. Whereas here you have all these mixtures. You have 2 times, we have 2 and 3 and 4, and 6 is 2 times 3, and 12 is 4 times 3 and 5 times 3, and so on. And so in this way you have many more Dirac measures which you can use, which are living on a subgroup with the Fourier transform being another Dirac measure up to the normalization living on the orthogonal subgroup. So I have to go back here and tell you, here it was 12 and have 12 things. And if you take the number of terms that you have here multiplied with the number of terms here, or reciproc, you're saying what is the distance here? Well, the distance between two such Diracs is exactly the number of terms that you have here in between terms. And what is in between here is the number of terms on this here. So the product of those two numbers, like 12 times 40 or 40 times 12, is always n. And that, of course, is only meaningful in the integer domain when you have a divisor of your signal length. Now, if I go back, oh no, it disappeared. Yeah. Not sure, seems to be a little bit. So I would like to show you once more the signal, maybe with DC3 and x pointwise with DC12. This is exactly what we would like to do in a mathematically correct setting. And I run it again. Oh, what's going on? Oh, okay, sorry, it would not point, but point was product. I was missing the stars here. And run, yeah. So while I'm showing you the sampled versions with sampling distance 3 and 12, sorry. It was working before. I'm not sure how, probably I should do a new line, but so what you, yeah, okay, so that's a good example. So here you're seeing the sampling with sampling rate 3, which is, of course, plenty of information, easy expected recovery or so. And on the other hand, you're seeing the sampling by 12, which is, I mean, if you do compare the piecewise linear interpolation of what you have to the left, it's very plausible that you're missing some information. On the other hand, certain features, like the peaks in the complex valued part here, which are repeated 12 times, but are still okay here. Now, you can imagine that if you are repeating with distance 12, then of course there is some overlap. So the copies of these things are overlapping. So what you would see if you would try to do reconstruction with this very sparse sampling, that's what we would, engineers would say, we are sampling below Nyquist rate. It's not possible anymore to unmix from the periodized version of this spectrum to get back to the original block. Whereas if you sample with 3, and also we have seen 6, you still have very nice separate copies. Now it's everybody. So let's maybe do the recovery from this last statement. So I would say field 30 is field symmetric rectangular of size 30. So maybe I'm doing F2 spec Gauss function. No, maybe XX and field 30. Hope it runs. So you should see the same plot, but a second plot coming up, which shows you, yeah, here, that this function is, okay, yeah. We're having the rectangular filter on the wrong side. So you would expect, but I don't want to repeat it now, that this rectangular function, which is having exactly the same boundaries as this supporter. So if you multiply the spectrum, the Fourier transform of this with this here, you're cutting out exactly this piece. And so of course we know that multiplying on the Fourier transform side with the rectangular function is the same as convolving with the sinc function on this side. So I would like to do the following. We're doing F2 spec. The original one is XX with DC3. So I'm showing you the original function. And then what I'm doing is I'm doing on the Fourier transform side. So at the end, I have to do an inverse Fourier transform. I'm doing the FFT. I'm taking the sampled guy to the Fourier transform side, DC3. And then I'm multiplying the pointwise sense with the filter of size 30. I'm not sure. I hope I have not forgotten any bracket. So I'm giving you a visual MATLAB kind of based proof, of the recovery of the sampling theorem in kind of an experimental way. And the goal really will be very soon to verify that the same thing can be done mathematically correct using these matrix distributions. But the first thing is, if we start from this smooth function and we sample it, we get this fragmented version of it. We have seen that sampling by 3 means you have 3 different copies. Now you have to think what I was doing is we're starting from this data, from the sampled information, of course, knowing exactly where these samples are. So they are not just a sequence of lengths 480 by 3, but it's embedded into the full signal length we are obtaining and throwing away all the values which are not on this lattice marked by DC3. But on the Fourier transform, sampling corresponds to periodization. Now, how can we get from a periodic version to an original version? We cut out. You also see that there are many ways to cut out. What we have to do is we shouldn't say we reproduce this. For example, we might not know exactly in this concrete case that the original function was so smooth that the maximal frequency was 30. Maybe we thought the maximal frequency is 47, and to be safe, we would take a filter of size 50. That wouldn't change the picture. It would still kill these frequencies, these very high frequency parts here, which more or less allow to produce the jumps, but the original part would be still cut out. Well, what would be the difference with this pointwise multiplication with a bigger rectangle? Well, this is a slightly stretched version of the original rectangle, and that would correspond to a higher oscillating sinc-like term on this side here for doing the interpolation. And so we will write down what does it mean on the time side now to come from the sampled function. which is very similar to our deep psi mu. It's a discrete measure that we take now, and that discrete measure has to be convolved with the inverse Fourier transform of the filter or so. Now, this is very nice and or allows us to recover us as long as these overlapping, these periodized things are not overlapping. And that's another very natural aspect, of course, that you might have in real world a situation where your spectrum is either not exactly concentrated well enough, so you have some tiny tails, or where you have really unavoidable overlap. So you have sampled a little bit too coarse, and that's the critical sampling rate here, of course, would be, we have, in our case, I would say for a demonstration in this example, I would say our spectrum is had width 61 samples. So 8 times 61 is just a little bit too large or so. So maybe if I should have taken a frequency of maximal frequency 29, and we would have 59 samples going from minus 29 to plus 29 or so. Then we could afford a sampling rate of 8, which is a close by. But if we would do the same thing, I don't want to do it now, we are close to the end, I would say that you would probably see a mild overlap. The biggest and the smallest frequencies are overlapping, and that would result in an aliasing error, which is probably not too big because we have about 60 Fourier coefficients and only 2 or 3 of them are overlapping and making a little bit noise. What you also see here is that if you would do it locally, so assume I would not have all the samples here, but I would have samples only from minus 100 to plus 100. Of course, you could say, well, then I'm convolving according to this formula that assumes I know everything. I would use only those samples which I have. Then the bed decay of the sinc function would be a disaster, or would give a suboptimal result, because the samples that I'm using give contributions which are giving spurious elements outside of the interval where I've sampled, far away even. And that means, well, we should use building blocks for the reconstruction which are better concentrated. And then it's good to know that better concentration means we should do something which is doing the cutoff theorem, cutoff property, which kills the wrong frequencies, but is better concentrated in the time side, which means it's more smooth on the Fourier transform side. So we will see, or that's also experimentally easily showable. If we take a trapezoidal function, we may be starting here, going up here in a smooth way and going down. Well, how do you get such a thing? Maybe we do some rectangular function which is a little bit wider, and then we smooth it out with a bump function with something like a B-spline of order 4 or higher even. And you will see that building blocks are much better concentrated, so that it's not only a summation if you have all the samples, but you have a better localized version. What you also see is that, of course, you cannot get a very coarse sampling at the maximum sampling rate and high concentration. So the more space you have here, the more local reconstruction can you have, but also the more closer the samples will appear, which also makes it clear that you can cover the gaps and you can do the good interpolation stuff. But if you're having gaps which are too big, of course, your building blocks have to be a little bit broader, and this picture gives you a good balance between these things. I think it's a good place to stop the experimental part here, and I will do such things also further on. Probably I will try to do a version of this here and store it so that you can run the same experiments yourself. Thank you for your attention, and I will now stop the recording.